Hi, and welcome to the Explaining Science video on astronomical coordinates. What I'm going to cover here is the standard coordinate system known as celestial or equatorial coordinates. These are the standard coordinates used on star charts found both in books and on the internet. For example, here shows the area of the sky around the constellation Orion. I'll talk about how we transform these coordinates from the coordinates found in star charts to the actual coordinates in the sky at a given point in time. The azimuth, which is the angle from the North Pole, and the elevation, which is the height in the sky. I'll talk about how the coordinates of stars and planets change over time, and I'll also cover other coordinate systems. The celestial sphere is an imaginary sphere with the Earth at its centre. It lies a great distance from Earth, so on this diagram it's not to scale at all. The Earth would just be a tiny dot with this celestial sphere wrapped around it. Because of the vast distances of the stars are effectively fixed on the celestial sphere, although they actually move very slightly. But objects in the solar system, such as the Sun, planets, asteroids and comets, do move. The North Celestial Pole is an imaginary point in the sky. It's a projection of the North Pole onto the celestial sphere. Lines of declination are a little bit like lines of latitude on the Earth, and lines of right ascension are a little bit like lines of longitude. The 0 point with declination 0 and right ascension 0 is the vernal equinox, which lies in the constellation Pisces. The north celestial pole has a declination of 90 degrees and the south celestial pole has a declination of minus 90 degrees. The Earth rotates once every 23 hours, 56 minutes and 4 seconds. That's a period of time known as a sidereal day and is slightly shorter, obviously, than the familiar day we use of 24 hours, which is based upon the rising and setting of the sun. If we were to stand at the North Pole and look up into the sky, we would see that all the stars moved in perfect circles around the North Celestial Pole. It would take one sidereal day to complete a complete circle. Stars of lower declination would move in larger circles lower in the sky. If we go to a lower latitude, such as 50 degrees north, then we can see that the stars rotate again around the North Celestial Pole, which is near the bright star Polaris in the constellation Ursa Minor, the small bear. Stars rise and set. And of course, later in the day, the sun rises, so it's daylight, so you can't see any stars. Okay, now let's look in detail of the path of a star having declination 35 degrees, observed at a place with latitude 45 degrees. The star rises in the east, moves higher in the sky, reaches its highest point when it crosses the meridian, which is the imaginary circle joining the zenith, north and south directions. It then descends and finally sets in the west. If we look at another star, this time at a lower declination on the celestial equator, it follows a similar path, rising in the east, setting in the west, but doesn't reach so high in the sky, and is above the horizon for a shorter amount of time. What we want to do is to work out a star's position when seen from a place on Earth. By this we mean its azimuth, which is its angle from a northerly direction, and its elevation, its angle above the ground. Today, many amateur astronomers have the telescope on a GoToMount. A GoToMount will have a database of tens of thousands of objects with their celestial coordinates, and the telescope on such a mount will automatically find and follow a source once the name of the source has been entered. But even so, it's still interesting to think about how we go from the position in a star catalogue, RA and DEC, to the position in the sky. The Earth takes 23 hours and 56 minutes to make a complete rotation on its axis. However, a solar day is on average 24 hours long. This is because during the time it has performed one rotation, the Earth has moved around the Sun a little in its orbit. For example, if we take the point in time when the Sun is at its highest in the sky, marked with a purple dot, then one rotation later, because the Earth has moved along in its orbit, the Sun isn't overhead at this point. It takes an extra 4 minutes for the Earth to rotate a little further to reach the point where the Sun is once more at its highest in the sky. And that's why a day is on average 24 hours. So the time taken for the Earth to rotate once on its axis is a sidereal day, and this is, as we've just seen, slightly shorter than the day we use in our normal day-to-day lives, which is the mean solar day. A sidereal day is divided into sidereal hours, minutes and seconds, each of which are slightly shorter than our normal hours, minutes, seconds. And the sidereal time at a given location on Earth is called the local sidereal time, and the local sidereal day begins when the vernal equinox, that's the point on the sky with 0 RA and 0 DEC, crosses the meridian. And at every given instant, all places at the same longitude have the same LST. As the sidereal day is a bit shorter than 24 hours, the difference between civil time and LST varies. So if we take Manchester, on the 8th of January 2023 at 11 o'clock, the local sidereal time was just after 6 o'clock in the evening. But later in the month, the local sidereal time at 11 a.m. had advanced, so it was 1932 roughly. There are lots of internet sites out there which give you, for a given location, the local sidereal time. The other thing we need to talk about is the hour angle of an object. This is the elapsed sidereal time since a star crossed the meridian, and it can be expressed either as a time or by multiplying the value by 15 as a number of degrees. When it crosses the meridian, the hour angle of an object is 0, and as the Earth rotates, the hour angle of an object increases. So if we look at how the hour angle of an object changes over a sidereal day, starting at 0 hours when it's at its highest, between 0 and 12 hours, the object sinks, reaching its lowest elevation at 12 hours. It then rises, reaching its highest elevation back at 0 hours. Hour angles of greater than 12 hours are commonly expressed as a value subtracted from 24. So instead of saying an hour angle of 21 hours, we say an hour angle of -3, 3 hours to midnight. Instead of saying an hour angle of 22:30, we say an hour angle of -1 hour 30 minutes to midnight. The hour angle is quite simply the local sidereal time minus the right ascension. So if anywhere with zero right ascension on the celestial sphere, the hour angle is equal to the local sidereal time. So now we've got hour angle out of the way, we can explain how we get from hour angle declination coordinates to azimuth and elevation. That's distance from north, and angle above the horizon. There's a number of steps in this transformation, so rather than repeat them here, you could just have a look on my blog site, which I put the URL below. So we can ask the question, what is the minimum declination of a circumpolar object? That's an object which never sets, is always above the horizon. Using these formula, we can work out, put the following values in. Well, obviously the object says its lowest elevation at hour angle of 180 when it just hits elevation 0. We know its latitude, so we want to find out the minimum declination. So putting these numbers in, then we get 0 equals sine dec times sine lat minus cos dec minus cos lat. We know from high school that cos dec plus lat equals cos dec cos lat minus sine dec sine lat. And we can use the fact that the cosine of 90 degrees is equals 0 to give us that dec plus lat equals 90 degrees, i.e. the minimum declination is the latitude subtracted from 90. The effect of the Earth's atmosphere is to reduce the amount of light getting to observer at low elevations because such light has to pass through more atmosphere. So perhaps instead of saying an object of elevation 0 is visible all the time, we should perhaps regard elevation 3 degrees as being a more realistic limit to say this object is visible all the time. So if we rerun the calculation we've just done, and rather than work out what declination it has to be to never drop below 0 elevation, let's do it for a more realistic 3 degrees elevation, which takes account of extinction by the Earth's atmosphere. In that case, the minimum declination an object needs to be never to drop below 3 degrees above the horizon is 93 minus the observer's latitude. The other thing we can work out is what is the maximum elevation for a given latitude and declination. I've put the working out here, so if you want to just pause and have a look at it. And you can see that the maximum elevation is the inverse sine of the cosine of the declination minus the latitude. Interestingly, objects with a declination of the latitude minus 90 degrees reach a maximum elevation of 0, so they just touch the horizon. Objects with a lower declination than this will never rise. So for Manchester, England, which has latitude 53.5 degrees, any object with a declination below 36.5 degrees south will never rise above the horizon. So here's an example of using these formulas for places at different latitudes. As you can see, as you go down to lower latitudes, less and less of the sky is circumpolar, but at the same time, the portion of the sky where objects never rise at all also gets smaller. There's extreme cases of the North Pole and the equator, which I'll talk about now. An observer at the equator will see anything at the north celestial pole or the south celestial pole completely stationary, sitting on the horizon, neither neither rising nor setting. Every other object rises in the east and sets in the west, as you can see by the red dotted lines or the blue dotted line, which just marks the celestial equator. The entire celestial sphere is visible, and all objects are above the horizon for 12 hours and below the horizon for 12 hours. Although, of course, objects very close to the horizon are difficult to see because of atmospheric extinction, which we've talked about before. And this time, imagine our observers at the North Pole. What they'd see is anything at the North Celestial Pole completely motionless directly overhead. All other objects would move in circles, having constant elevation, never rising, never setting. Only the northern half of the celestial sphere could be seen, and objects with a declination above zero would move in these constant circles, so they'd never set. Objects having declination below zero would never rise. So far, we've just talked about coordinates of stars. Now, stars don't move on the celestial sphere, or rather they move extremely slowly. If we consider objects in the solar system, then obviously the Earth goes round the Sun once a year. So the position of the Sun as seen on Earth, seen from Earth on the celestial sphere, is constantly changing. And the same is true of the planets, because these are also moving around the Sun. Because the Earth is moving around the Sun, it means as seen from the Earth, the Sun appears to move around the celestial sphere. So if we look at the celestial coordinates of the Sun over time, then in March at the equinox, it is 0 RA, 0 dec. It goes up to 23.5 degrees declination at the June solstice, back to 0 declination at the September equinox, and in the December solstice it is at its lowest declination, 23.5 degrees. It's this change in declination of the Sun, which means that the Sun follows a different path through the sky at different times of year. Let's look at the view from Ankara in Turkey. In June, then the declination of the Sun is 23.5 degrees, and it gets very high in the sky and is above the horizon for a long time. Whereas if we go to December, then it's much lower in the sky and it's above the horizon for only 9 hours and a bit. Because the planets are moving around the Sun, as well as the Earth moving around the Sun, the motion of the planets across the celestial sphere is a bit more complicated. They still stick to the plane of the ecliptic, but the rate at which they change right ascension and declination varies throughout the year. You can see this on this chart of Mars's position. From January 15th to February the 15th, it only changed 26 minutes in right ascension. But if we go to the period from June the 1st to July the 1st, it changed nearly an hour in right ascension. Well, I hope everything we've done so far is clear and easy to follow. There's just a few more things we need to consider before we've completed our coordinate transformation to azimuth and elevation. Over a period of time, the alignment of the Earth's axis gradually changes with respect to the distant background stars. The bright star Polaris is the current North Pole star, but the movement of the North Celestial Pole over time means that by the year 14,000, the North Celestial Pole will lie quite close to the bright star Vega, and Polaris will be nearly 45 degrees away from the North Celestial Pole. The effects of precession are that it causes the celestial coordinates of stars to gradually change. This doesn't mean the stars are moving. All that's happening is the coordinate grid we're measuring them against is gradually drifting. The movements of a star's position on the celestial sphere is actually quite large, 1.4 degrees per century. And in 13,000 years' time, the star, which is now our pole star, Polaris, will be only 43 degrees north. So because of this, when we specify RA and DEC, we must specify them for a given time, and the standard is 12 o'clock on the 1st of January in the year 2000. So far, we've regarded stars as being stationary, but stars do actually move very slowly with respect to each other. We call this apparent motion of the star across the celestial sphere, as seen from Earth. The proper motion is relatively small, and it's only really significant for nearby stars. It's typically measured in arc seconds per year, and there are 3,600 arc seconds in a degree. The brightest star in the night sky, Sirius, lies at a distance of only 8.6 light years from us, so it's one of the closest stars, and shows a significant proper motion. But even so, this proper motion is only 1.339 arc seconds per year. It would take 2,700 years for Sirius to move 1 degree. Another thing I want to talk about here is something called stellar aberration. There's a separate video on this topic on my YouTube channel, so all I'm going to do is a quick overview here. The Earth is moving rapidly around the Sun, over 100,000 kilometers an hour, and this causes a slight shift in the apparent position of the star. It's actually been known about since the 18th century. This effect is a bit like when you move very rapidly through rain. You need to tilt your umbrella slightly forward in the direction of travel. Final thing I want to talk about in detail is something called stellar parallax, and this is a very small shift in the apparent position of a star over 12 months caused by the Earth's changing position in its orbit. And it is a small effect because the stars are so far away compared to the diameter of the Earth's orbit. The closest star to the Sun only shows a parallax of 0.77 arc seconds. So to sum everything up, if we start with the J2000 coordinates in a catalogue, we need to correct for proper motion of the star, stellar aberration, precession, and something we've not talked about before, but it's a small wobble in the Earth's axis over a period of 18.6 years called nutation. Relatively small effect. This gives us the coordinates if the star was observed at the centre of the Earth. What we then have to do is correct for something called diurnal aberration. That's because the Earth is rotating, and this causes a very small shift in position, and it's only really important near the equator where the Earth is rotating more rapidly. With this then gives us the local coordinates for our location. We can convert these to azimuth and elevation as we've described before, and we then need to do another correction for refraction, which is due to the fact that at very low elevations, light is bent. And after that correction, it will finally give us what we want, the observed azimuth and elevation.